And I'm going to talk about classifiers and classification. I get to do this talk because I'm the guy that designed the API for the classifiers. Matt actually is responsible for, I'll be nice, the original, the original versions. But there's a lot of power in them, and I'm going to try and show you how to use them. Before we start, the question you should be getting in every session, who's a brand new Earth Engine user? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Wow, OK, half. A little more than half. Who considers themselves an advanced user? All right, so we'll be leaning towards the basics here a little bit. It's really the same presentation either way, but yeah. All right, so we're going to be talking about supervised learning. The majority of our classifiers are, in fact, supervised learning. And when you're working with supervised learning, you're basically training with and classifying feature vectors. And what that basically means is a table. So each row of the table is a feature. Each feature has a set of properties, and all those properties together are the vector that you're either training with or classifying, sort of your independent variables. Under supervised learning, we also have a class variable in the vector that says, during training, this is class 0, or this is class 1, or this is class 2, so that the classifier can learn what those classes are. And that's the whole point, is to be able to give it a bunch of classes and some features for those classes and say, OK, now that you've learned that, where do you think these go? Some constraints on our system. We don't allow sparse training data. So when you're training, you got to have fully populated features. If you have some masked pixels in your image and you're sampling from those, and you don't have an elevation value for one of them, the training data, it'll blow up. We just don't allow that. Sample, if you're using it, will actually throw these away. But the classifier, if any of these get to the classifier will say, too bad, I'm not going to let you do that. The classifiers are basically scoped for about 1 million features. If you're trying to do more than that, you're probably going to run into some problems. And those are 1 million features of a size about that big. If you have 100 values in your feature, you're going to be able to fit a lot less of them in memory. If you have 2 values in each feature, you might be able to fit more. But the general rule of thumb is you're shooting at about 1 million points for training. The way the classifiers work is that you train them up, and then you sort of paint with them. You've trained it how to do its thing, and then you can just paint with images, or paint on top of images or tables to say, what do you think all these things are? So it's about 1 million points to train, and then you can do billions or trillions of points once it's trained up and do entire global classifications. They're also all built for a small number of integer classes, so essentially 0 to n, classes 0, 1, 2, 3, 4, 5. If you skipped 4 and it was 0, 1, 2, 3, 5, that's OK. 0, 5, 10, that's OK. 0, 10, 1 million, bad things happen. The system allocates things up to the maximum number in your list of classes, and so you're going to get 1 million things allocated in there that just won't work. You'll get 1 million pixel or 1 million row wide confusion matrix at some point. It's just a bad thing. So generally, you're going to have to bring your numbers down to a small number of integer classes near 0. OK? You with me? All right, so that's what we're doing. The classification workflow in Earth Engine is pretty simple. You build a classifier, you train it, you apply it, and then maybe you do some assessment. And actually doing it looks like this. Can you read that? Is that? OK, great. So the very first line is just getting some training data. So maybe you've already got a table of training data. Maybe you want to sample it out of an image. Wherever you're going to get it, you need a feature collection with a bunch of features in it that are your training data. And then the rest map straight to 1, 2, and 3. You build a classifier by calling ee.classifier.name of classifier, and you train it with the train function. Pretty simple. You apply a classifier to an image by saying image.classify. It doesn't get any simpler than that. You can ask the classifier for a confusion matrix. Once it's built up, you can say, based on all your training data, reclassify your training data and tell me how well you think that worked out. So a cross-validation with the training data. And then once you've got a confusion matrix, you can get some accuracy assessments out of it. So if you like, we're done. You can go. This is all you need to know. But I'm actually going to tell you some details about how this works so that when you run into problems or you want to do something weird, you know how this, you know what's going on and might be able to do it. But this is really all you need to know. Building a classifier, as I said, e.classifier.name of classifier. And some of these classifiers have a bunch of options. Cart's one of the most egregious here. The classifiers that we have are all so famous that each one of them has its own Wikipedia page. So we don't go into a lot of detail about what cart is and what all these things mean, because it's just a reference implementation from, or it's an implementation from the reference. So if you go look up how carts work and whatnot, they're a tree, you can prune them, that's what the prune parameter is. There's a population to split them, that's what min split population is. So in a lot of cases, we don't explain these in great detail. We tell you what they are, we give you a sentence description, but we also give you a link to the Wikipedia page or the original paper where these things came from, because they can tell you a lot more than we're going to be able to tell you in the little box where we give you docs. Almost all the classifiers will work out of the box with no arguments. And that may be true for all. There's one that won't work. But so you can try it out with just building a classifier, no arguments, see how it works, and then you might want to tweak it to get better results. Our classifiers can do 3 different things, some of them. There's a straight up classification, which is discrete values. So this is class 0, this is class 1. They mean completely different things. There is no class 0.5. So that's called classification. There's also a regression mode, which involves continuous numbers. So if you have percent tree cover and you're trying to do a regression to be able to predict percent tree cover from some covariates, then you'd be using regression. So that's continuous variables. And then some of them have this probability mode where you can say, what's the probability that that was the class once you've determined it? And right now, these only work on binary classifiers. It's basically the probability of it being class 1 when you have a 0-1 classifier. We might actually be changing that because we think we can do multi-value probability, but right now it's just binaries. Not all of them support regression. Those 3 do. And not all of them support probability. Those 6 do. So when you get in there and you need to know those details, there you go, details. You just call set output mode. Once you've built a classifier, you can just call set output mode on it to switch between these things. But be aware that that's basically building a whole new classifier when you do that. Your regression classifier that you switch into probability mode is not really just, it looks like it's just a switch, but it's building a whole new classifier. You might not care, but just know that at that point they're sort of unrelated. The caching's different, all that stuff. So it's essentially building a whole different classifier in the process. We good? Great. So most of the art in building a good classifier is in picking your training data. So much so that it's called training engineering. The way that most remote sensing guys do their training is pretty standard. So I'm going to walk you through how that's most commonly done. But there's a million different ways to do it. So I'm just going to give you some tools and then let you hurt yourselves with them. We have 2 functions specifically for sampling from an image. The first one's called sample. You just give it an image and a region, and it will give you every pixel in that region out of the image. Every band in the image becomes a property. Sample can do subsampling, so you can say, just give me 1,000 points in this region, and we will either generate 1,000 random points and sample them, or we will sample every single point and then do some random sampling on, we'll throw away, if you want 10%, we'll throw away 9 out of 10. And it depends on how many points you've asked for relative to how big the region is. But just be aware that they might come through different paths. One might come from random points, and the other might come from randomly selected exhaustive points. Sample specifically discards sparse features. So I have 3 times now debugged the same problem. I just forget every time it happens, where someone is trying to gather a bunch of training data from late 2015 from Landsat 8. Landsat 8. Turns out the thermal band didn't work at the end of 2015, and so if you're sampling from December, you've got a blank band 10, right? It's all masked out. And so every single feature that you get with sample has a sparse feature vector, and we just throw them away. So you sample this image, and it returns nothing. It's like, what's going on? And I immediately think I did something wrong, and I go spend hours figuring that out. And no, it turns out, 2015 band 10s are bad. But be aware that it will do some silent discarding. We're actually talking about making it not so silent, like maybe putting on the collection that comes out an indicator, a piece of metadata that says 47 points were discarded due to a null value in band 10. But that's not there yet.
Does that affect masked values?
Any masked value that you tried to sample will be discarded. And even if it's not fully masked, if just one band is masked, it gets kicked out. Because sample was built specifically to go into training, and training won't let you have masked values or null values. Yep.
Can you import from libraries?
Import from libraries. What do you mean?
Spectral libraries.
Spectral libraries.
Well, let's say that I already have the most sensitive.
Yeah, if you stick them into a fusion table, then you can bring them in and use them that way. So yes. All right, so there's another function called sample regions, which was built specifically because there's a slightly different workflow that people do all the time. What this is you'll have a big polygon that's called farm and a big polygon that's called city, and you actually want a bunch of features that take that property along with it. So sample all the points in this farm polygon, and you'll get a bunch of points that are labeled farm, and sample all the points in this city polygon, and you'll get a bunch of points labeled city. And so you're actually propagating properties from the input features to the output features. And so this is a slightly different workflow, so there's a slightly different function for it, and it's sample regions that does this. Just like sample, each band becomes an additional property, but this one doesn't allow random sampling because the intent is you're sampling from different things, and they may be different sizes, they may be 1 point in one case and a giant polygon in another, and so it doesn't support random sampling directly. I'll show you how to do some of that later if that's what you want. But you use this when your input features have stuff that you want on your output features. In 2015, this is what sample regions looked like and what people did. So I point this out specifically because if sample regions doesn't quite do what you want, or you need something close but slightly different, then you can always just go run it in the JavaScript yourself. This is exactly what the internal version does. And so you can now modify this and do something different if you want. Do I need to go through that? Anybody want me to go through that? Great. All right, so it's very common that you'll want to do random sampling because we only allow for 1 million points. So if you've got a 1 billion point region and you want to just get 1 million points out of it, you're going to have to do a factor of 1,000 decimation on that. So one way you can do that is that sample takes number of pixels. You can just say, give me 100,000 pixels in this region, period, and it will figure out how to do that. The other option is that you can say, here are 100,000 random points, go sample those. But if neither of these are doing what you want, and for instance, you need to subsample from data that came from sample regions, then this is how you go about it. There's a function specifically called random column, or a function called random column specifically to stick a random value into your feature, and then you can filter based on that value to just get 10% of your input. You might use this for decimation, but you might also use this to do your own k-fold cross-validation. So you can take a different 10% each time, train with the other 90%, and validate with the held out 10%. You can do this yourself. It kind of stinks, as pointed out. So we'll probably be adding a function to make it easier, but I just want to point out that you can do it. And even if we do make a function that makes it easier, it still may not do what you want. You may end up wanting to stick a random value on each feature and do something with it. Make sense? Good? Yes? No? Someone has to say something.
Yes.
Great. All right. Another thing people like to do a lot in our field is do stratified random sampling. So in this particular case, you're looking at a Modus land cover image, and the intent is that you might want 500 points from each land cover class so that one particular class doesn't dominate the classification for some reason. I was going to do multiple strategies on this, but the first one worked out good enough that I'm just going to show you that one. And if you want to do more, then let me know and we'll talk about it. But I'm actually going to demo this one for you. There's my land cover, there's my points, all in my polygon, right? So nothing crazy here. I'm trying to get out, in this case, I think I'm actually asking for 50 points in each class. But I'll show you what's going on here. So we'll come to the script here in a second. Is that legible, or does it need to be bigger? Bigger, okay, bigger coming, 1 second. How's that? We'll talk about it in a second. So we'll come back to that in 1 second. So I'm pulling out the Modus land cover, MCD12 images, sticking it on the map so you can see it. And then I'm running a frequency histogram over that in my region to tell me what classes are in here. Because I don't want to try and do a stratified sampling on a class I don't have. That's just not going to work. So I print out what that is. And it turns out that, in fact, all 17 classes happen to be in this polygon. But some of them only have a few points in them. This one's got 3, this one's got 27, this one's got 8,000. So now I've got a problem. I can't say, give me 50 points from the class that has only 3 points. Well, I can. I could replicate my points a bunch of times. So I'm going to just arbitrarily make a decision and say, I want up to 50 points in each class. Give me however many you got, or clamp it at 50 if that's what, if there's more than 50 in there. And I'm going to show you one method for doing this. It's a bit of a dumb method, but it works pretty good. So here we go. One more. So I have my counts, right, my frequency histogram, and that's a dictionary. And what I'm going to do is I'm going to map over each of those classes, each row in that dictionary, to then do something for each class. And so the first thing I do is that I mask out my image so that I only have pixels from that class. So it gets the first row is a 0, throw away everything that's not a 0 in this image, just mask them out, and now I've got an image that's nothing but the locations where zeros are. I then sample that, and we're going to skip this line for a minute. I'll come back to this line and a few lines below it in a minute, but we're just going to sample that image and we're going to massively oversample it. So I'm looking for 50 points, I'm going to sample 5,000. And this factor of 100 is just sort of a really bad rule of thumb that last time I had to do this worked out, that if I've got a sparse set of points, I need to oversample by about a factor of 100 to be able to make sure I get the sparse points. Because this is just throwing a bunch of random points on there and hoping that one of them lands on one of the pixels that is of type 0. And it turns out, for the things I was doing, a factor of 100 worked OK. A lot of extra work, but it works good enough. I'm setting a seed for each one that is the value of the class so that they aren't all exactly the same points. I'm asking for 5,000 points from each layer. If I just ask for that same 5,000 points over and over, it'll kind of work, but I actually want a little bit different here. So sample over all of them to oversample. Now, I could stop there. I could just say, OK, give me the first 50 points and I'm good. But when I'm sampling this many points, it's not using random points. It's starting at the top of the raster and going to the bottom. And so it's giving me 5,000 random points, but they happen to be spatially oriented. So the first ones are at the top, the top ones are in the front, and the bottom ones are at the end. So I actually kind of need to mix them up a little more. So in this case, I'm actually going to use random column again, just to give each feature a random value, and then sort on that thing. So my random points, which were not quite so randomly oriented, now they are randomly oriented, and I can just say, give me 50. So limit that collection to the first 50 points that come out of that, or the minimum of the class that I had, or the first 50, because I don't want more than that. And that, we'll discuss those others in a second, looks like this. So 50 for most of them. For the ones that are less than 50, I get less than 50. For my one class that only had 3 points, I only got one of those points. And so I could be a little more clever about that one and just say, don't random sample that one, actually do exhaustive sampling on that one. But this works. This got me what I needed to have. And you now can use this same script to do what you want. This bit in the middle that's a little weird is a workaround because sample and sample regions don't give you points with geometries because they take memory. So if you want to fit 1 million points in memory and each of them has a geometry as well, that geometry also takes memory. So we've got 1 million geometries, and if you didn't want them, that was memory that you shouldn't have been wasting, because memory is kind of expensive on us. So when you do want them to have geometries, because I wanted to stick them on the map and kind of look at them, this is how you go about it. You add a lat-long layer to your image, so there's 2 more bands, 1 latitude, 1 longitude, and then for every feature, it will now have a latitude column and a longitude column, and we make a point out of those 2 points, 2 values, and make a new feature that has that location and all the values from the original feature. Okay, so it's a common enough thing that this has been on the list maybe 10, 15 times now, that if you want to stick points on one of these things, this is how you go about doing it. Now you have a link to a script that will let you just grab it and use it again. This whole thing returns, so this was mapping over a dictionary, so each value in the dictionary has now been replaced with a feature collection. Flatten all those things out by getting the values out of the dictionary, and then flatten all those collections together into one big collection with flatten. And it looks like that. Okay? Make sense? So when you build a classifier, you have to tell it some training data with built-in classes. And so this is getting classes from something so that you can say, these pixels are water, these pixels are urban. It has to know what you want to call those pixels. You want to group them together. And so this is giving them some classes. Often, yeah. Depends on who you are and what you do. In that case, you would have points that came with a class, so you could just do sample regions directly on top of the Landsat imagery, for instance, and never bother with this MODIS data. But I wanted classes, so. Okay? All right, we're gonna go forward. And as you're probably aware, being this is the 4th session you're in, all the presentations are on the website, and they all have links to the examples, so you can get back to them. There's the stratified random sampling as code. Once you've got some training data, however it is you go about getting it, then you train your classifier with it. A couple things to note. Once you train a classifier with some data, that sets the classifier schema. And the classifier is then built for that. So if you give it 10 bands to begin with, it's going to expect 10 bands from then on. Anything else you do with it needs to have those same 10 bands. This is one of the very few places in the system where we match things up by name. So if you give it an image with bands B1, B2, B3, B4, B5, it's going to say, my schema is B1, B2, B3, B4, B5. And if you give it another image that's red, green, blue, near IR, SWIR, it's going to go, I don't know what those are, cut it out. If you give it another image that has B5, B4, B3, B2, B1, it's actually going to put them in the right order by name. Very uncommon, but the flow for classification just made more sense to do all this matching by name. So just to let you know, it's done by name. There are some subsampling options inside of train. I don't see that anybody has ever used them because there's all this other different subsampling that happens. And more importantly, when you train a classifier, this actually doesn't build the classifier. It doesn't actually do anything. It just associates some data with the classifier. And so you can actually do that several times. You can train the same classifier with 4 or 5 different feature collections if you want, and they just accumulate. When you actually go to build the classifier, when you go to use the classifier, it has to get built, and that's when all the data is pulled in. And so you can actually use this to your advantage when you're trying to use more data than is perhaps allowed. You can actually, rather than make all your data in one giant monolithic pile, which may cause problems with some parts of the system, you can actually train it with several smaller pieces and maybe sneak around 1 or 2 of the limitations in the process of doing that. Just maybe. All right, any questions yet? Okay, in theory, we now have a trained classifier in hand. It's got a schema, and we're going to do something with it. So classifying an image, as previously mentioned, is dead simple. You just call classify with the classifier. There aren't even really very many options here. The bands have to match by name. It adds a band to your output called classification, but you can change that name with the one other option. And this will allow for incomplete feature vectors. So if you have masked pixels here, it will just sort of gloss over that. It will give you the best answer for what you do have, but this can cause problems because if you give it a completely masked pixel with no values, it's going to assign it to some class. And you have no idea what class that was or whether it was a good assignment or not. So you'll have a lake in your image and nothing else. Everything's masked out. And you classify it, and suddenly your image is all white because both the lake and the non-lake all ended up in the same class. Well, that's not what you wanted. So it's really common that when you do this, you'll want to put the mask from the original image back on the classified image. So if you've masked off all the stuff that's not a lake, or not in your Everglades or wherever it is, and it goes ahead and assigns some class out there, you'll just stick the mask back on the classifier to get rid of all that stuff that was junk in the first place. Make sense? Okay. You can also classify tables. So you train collections with tables. You can also classify them. Works exactly the same way. Classify, table.classify with your classifier. Does the same things. Properties are matched up by name. It adds a property named classification, or you can pick what it is. Both the images and the tables can have extra bands or extra features. They'll just be ignored. And that's what the schema is all about. If you train with a 10-band image, but then you try to classify a 20-band image for some reason, and all the names match, it will just throw away the other 10 bands, use the ones at once, and let you keep going. Same for the tables. Good? This is going to go really fast. All right. So assessment. How did my classifier do? You can ask a classifier for its confusion matrix. What this will do is it'll take its training data, it will classify all the training data, and then it will compare the predicted, the value that comes out of the classifier, the predicted value, with the actual value that was already on the training data. So you said this was class 0, and it gets classified and it says, nope, I think it's class 1. Well, that's confusion. And so you can get a matrix of inputs versus outputs. It's basically just a big array. And you can also say, based on that matrix, what's my accuracy, what's my producer's accuracy, what's my consumer's accuracy, and what's a kappa value. People have been making these confusion matrices by hand because we allowed it. There's a big note in my code that says, no one will ever try this. Don't bother testing this path. Turns out I was wrong. People are trying it left and right. Beware if you're making them by hand. Look, there we go. So the confusion matrix is very specifically cross-validation with training data with itself. You might have a validation data set that you want to get a similar matrix with. It's not really a confusion matrix at that point. It kind of is. We just didn't want to mess up the namespace here. So you can actually ask a table for an error matrix, which just returns a confusion matrix object. This is where you'll have, for instance, some points with hand-validated, hand-picked classes, and you can then classify those points and say, well, how did my predicted value go with my actual value? So you just match up these two properties in every feature to get an error matrix that works exactly the same way as the rest. Okay, so other. So you now know almost everything that you need to know to use our simple supervised classification stuff to good effect. There's some other stuff in here that you might care about. So for cart classifiers, you can say, tell me your decision tree. And that's done with the explain function. Currently, cart is the only classifier that has a working explain, but as we can figure out how to do something meaningful for the other ones, we can actually explain more about them. So for instance, for support vectors machines, we can actually give you the support vectors. And for random forests, maybe we can give you the forest of trees. That's a lot of data, and we don't quite know what to do with that. But in this case, explain for cart produces a text representation that's standard for R created trees created in R. So you could cut this out, paste it into R, and use it. And vice versa, you can take an R-produced classifier, text representation, and shove it into Earth Engine and build a decision tree out of that. So this one produces them, this one consumes them. Yeah, I don't know how to do that. So if you can show me how to do that, then maybe. I do know that these are essentially ordered by importance. So I think that's the same answer. And you can just pull off the leftmost ones and the second leftmost ones. But this particular one, as you can see, had more than 10,000 or more than 1,000 nodes in it. So pulling those out might be unpleasant. But if it isn't just the left to right order of these for importance, then tell me how that works and we can add it. So we'll step through this real quick. What is happening here is that the text output from an R-built decision tree is uploaded into Google Cloud Storage as a text file. And then you can actually bring that in with the blob function. Go get that text file, bring it in as a big blob, and now let me do something with it. Currently, the only thing you can do with a blob is shove it into a decision tree classifier. But it parses it up, builds it, and now we can run that, we can paint with that classifier. Does that make sense? Do I need to go through that in any more detail? Wow, you guys are quiet. I live in Europe now, and I'll give a talk, and for the most part, depending on, there's a few places where it's not true, but for the most part, the Europeans just never say anything. And I was excited to come back to the US where everybody, yeah, you talk to me, but you guys aren't talking to me. Decision tree is a classifier we built. All the other classifiers that I've talked about so far, and except for the rest of the ones that I'm about to talk about, come from a library that Google has that we just use. So I don't know all the nitty-gritty details of those because I didn't write them. I just wrote wrappers for them. These I wrote. And so they're kind of weird. There's some weird ones, but they have a lot of useful value to them. This is a scatter plot from the JRC global surface water algorithm. It turns out that they do some decorrelation stuff, and in the decorrelated space, the water stands out in a nice, pretty polygon. Basically, there's a region in the scatter plot where all the water is, or all the clouds are, or something like that. They built themselves an app where they hand validate a bunch of points, assign a bunch of classes to a bunch of points, put them into the scatter plot, and then draw in that scatter plot a polygon. They said, this is where our water is. And then they have a function that will turn that polygon into a gigantic Earth Engine expression that tests whether or not something is inside or outside of that polygon. So for every edge of that polygon, there's a left or a right test. And so if you test the point against every single edge, you can say whether or not it's inside or outside the polygon. This turns into a 500-line Earth Engine expression. But they did a bunch of them, and we parsed them well, and it works out. But I'm like, dude, that's a really hard way to do it. So we wrote for them a spectral region classifier specifically where they can just stick the polygon in there, and we'll do all the crazy math. So in this particular, to use the spectral region polygon, the spectral region classifier, you give it your 5 points of a polygon or 10 points of a polygon, whatever that works out to be, and we just code that up as the big, long, ugly expression, but you never had to see it. This space basically goes from 0 to 1, and so you just, your polygon is from 0.3 to 0.7 kind of thing, and then it's just an inside-outside test that we do. But it's much, much faster than evaluating the big, long, ugly expression, and you don't have the big, long, ugly expression stuck in the middle of your script. And now you can use it. We recently released minimum distance classifier without a lot of fanfare. This thing supports various different types of distance metrics, Mahalanobis distance, Euclidean distance, and a spectral angle distance. And so with it, I was actually able to code up a spectral angle distance example, which is super simple. The way it works is that I've got some training points that I've plopped down, and all these are fed into the distance classifier as training data, and for each class, it just takes a mean of all the training points for that class. So I gave it 4 urban, or I think in this case road, four road points, and it's going to take the mean of all those road points and say, okay, that's one spectral point. And this is take the mean of all this forest. Now I've got a forest spectrum. That's my spectral point. And then it just maps the distance from every pixel in this Landsat composite to one of those classes. And so in this case, it's a cosine angle. So take all the features, do a dot product, and the closer you are to one of those spectra, the better your score. And it just gives you the minimum distance value here. It's a pretty common way to do spectral-based classification, and now it's super easy. And so if you have a spectral library, you can just feed it into this, and do a minimum distance spectral angle mapper. I guess, yeah.
So those dark patches, are those what the algorithm could match?
Nope, those dark patches are actually dark forest. I have some dark forest in here somewhere.
Okay.
Oh, no, I'm not true. That's not true. That's a great prompt. Thank you. If you, let me go back to my screen here for a second. In regression mode, the minimum distance classifier will actually tell you the distance. So I didn't want to add a whole new distance type, distance output type, so I just kind of shoved it into regression because I can't do regression with this one. And so, oops, go back to this again. I'll just bring it up again. There we go. What I've done here is I've said if the distance is greater than 0.3, tenth of a radian or something like that, 0.5, then it's too far away, mask it out. And so those are actually masked pixels. If I go to map mode, map mode, that one, right? So knowing the distance lets you assign some quality to the values. And it's like, okay, 0.5 is way too big, get rid of those points. So that's what those are. They're not actually forest, because I didn't have a forest class. Uh-huh. 2D, yep. The question is, will minimum distance, will spectral region be expanded to handle multiple dimensions? Probably not, because it uses a polygon. And doing a 3D polygon is a non-trivial thing. But tell me what you have in mind, and maybe we can do it. Explaining what your inside, what your region is in 3D is a goofy thing. But if you have a thought about that, talk to me, and maybe we can figure something out. The nice thing about the minimum distance classifier is it's really fast.
So another question. So if I'm interpreting that map correctly, your red was meant to be road?
Let me see. Yes, my red is intended to be, I think it might be urban.
Oh.
Yeah, I think it's just urban. I think I have some road pixels on here. Let's see which ones they are. I have class 2, which is this ugly yellow. So where's my ugly yellow training? Come on.
What I'm wondering is whether you can impose some...
You can get rid of points that don't match criteria like that. Like you could do a connected components on the resulting map and say, okay, anything that's not connected by four-way connection is clearly not road. Putting that into the classifier, I don't know how to go about that, except by computing a layer that is the connectedness before you do the classification. So train with a connectedness layer and then add a connectedness layer to your input for painting. Yeah. So if you were going to do something, that's how you do it.
Yeah, you didn't go through all the types. So
Okay, so I got one slide left, and much to the chagrin of all my guys, I am a strong proponent of always telling any group that comes to comes to hear one of my talks stuff that's coming up. So a preview of new features, and my team hates this, but I'm going to do it. So I've been working on unsupervised clustering stuff for quite a while. I built it on top of the Weka learning library. Turns out Weka is a piece of crap. But it was a lot of work, and I don't have other replacements for these things, right? Weka is basically a pedagogical toy. It's for teaching how to build classifiers, and it turns out no one that's ever built a classifier in Weka has done a good job of it, right? They were learning how to do it in the process, and so they all kind of stink in terms of memory and performance. That said, I got a bunch of classifiers, or a bunch of clusterers built on top of Weka, and we're fighting with the team. The team is fighting internally. It's like, well, do we release this thing that we know has all kinds of scaling issues, or do we wait until we can build something better? I've gotten 3 days of code, three days to write code this year. So I'm certainly in the camp of let's get it launched and let you know that it's got some limitations, right? You will probably not get a training to work with 100,000 points. It's probably more like 25,000 points, 20,000 points. If you're using LVQ, it might only be 5,000 points. It just takes a long time, and they might or might not run out of memory. But that said, several people, I'm looking at one of them back there, have been previewing this, and they said, no, this did what I needed to do. So that gave me confidence that maybe you guys could get some use out of this, even if it's a toy, until we can replace them with some better options. You want to say anything about your experiences?
I have 27,000 points that I was trying to get nearest me. I used them as a nearest neighbor sampling and worked fine.
Good. So yeah, for small things, it's working pretty good. Generally, my team hates that, but there's some value here to be had. So what will probably happen is that we will go ahead and release it and put all kinds of big warnings on it that you might hurt yourselves or us in the process. And then we'll just have an incentive to go put in some better versions. Mm-hmm.
For the unsupervised clustering or
Correct.
classification?
So it's about $1 million for the spectral, for the classifiers we built. The clustering that comes from Weka, you're never going to get 1 million points out of that. You're going to get.
You have an answered image, let's say, and you want to classify it. You have a problem doing that with these.
So it's always in the training. So you could sample 25,000 points out of your Landsat scene to build your clusterer with, and then, just like the classifiers, you can paint that over very large areas just fine.
Or point
Some kind of subsampling is what's going to have to happen for that kind of thing. But if for a Landsat scene, you just thought, well, yeah, okay, maybe I can get down to 25,000 points. That might work. But for a lot of our users, the answer is, well, for the entire United States, with a global composite, there's definitely some scaling issues here. So I'm at least going to show it to you, and then you can advocate for, hey, yeah, guys, release this thing. So that was k-means. It was a 15 class k-means trained with 5,000 pixels. So just to break the cache and run it again, you can see how long this takes with 5,000. Come on, go back up. A very anticlimactic end to my talk, waiting for the progress bar to end. Yeah, so that was 30 seconds or so. If you're doing 25,000 points, that's 2.5 minutes, 3 minutes. You could be approaching the timeout problems, interactive timeouts limits on that. So it's tricky. What Weka does, Weka has a classifier from clusterer, which you give it training points, and then it says, okay, in this group, it looks like most of them are 0. And in this group, it looks like most of them are 1, which is kind of okay, except when I tried it, it said, okay, in this group, most of them are 0. And in this group, most of them are 0. And in this group, most of them are 0. So I didn't get really great results out of it. What you might do is take this and then do something further with it to assign a particular meaning to those rather arbitrary clusters that come out of it. The people I built this for that were interested, they were actually just interested in the clusters. They didn't want to do the clustering after the fact. They just wanted to know where the cluster centers were. So that might be a thing that you want to do with it. Okay, I think that was my last slide. Yep, that was it. So thanks for coming.